Welcome back, everyone. I'm John Furrier, your host of theCUBE here in our Palo Alto studios for a special series with theCUBE and the NYSE Wired program and community featuring the GSA Series. We're unpacking the leaders' thoughts and commentary on the future of AI infrastructure, how data will be moving, and of course the applications that will sit on top that will power the next generation. The title of this panel is Memory and Data Movement for AI. We've got two great experts here. Cynthia Hsu, Senior Director, Flash Memory Design at Sandisk, and Amber Huffman, Technologist at Google, on the board of Open Compute and wrote many, many products. Thanks for coming on the program.
Thanks for having us.
I love this series because it's like we're almost covering the full stack of the action from the low-level silicon chips, and the data movement piece is very near and dear to our hearts because there's two major things going on right now. What does the memory design architecture look like in these large scale systems? And then two, the abstraction that sits on top that's going to power the most hyped up market right now, which is agents, which is, I think, is worthy of the hype, but still, it's coming fast. Those are two areas. Amber, you're on the board, you see the standards, you're on the board of Open Compute. The work being done at the infrastructure level to make things happen, it's not just about memory and storage, there's other things involved. Break down the memory and data movement space, if you will.
Yeah, standards is a really active space these days because there's so much happening, like with the boom that we're all experiencing right now, you can't possibly do it all yourself, right? And so that's where what standards bring us is we can each work on what are we good at are we great at doing a memory component? Are we great at doing a solid state drive? Are we great at building a whole rack? So in terms of breaking it down, what I'm seeing is a ton of work to figure out power, cooling, data centers is really where I'm spending a ton of time versus the memory itself. On memory, we've actually got a ton of great standards bodies where we look at NVMe Express, JEDEC, Open NAND Flash Interface. These have been established over the last 2 or 3 decades, and so we're building on those iteratively, whether we look at the solid state drives or the memory. Yeah. But power and cooling, going from a 48-volt rack, we're doing plus minus 400-volt DC. Yeah,
I mean, the innovation, it's this physical AI, I love that term because it kind of crosses two worlds, the facilities in the data center or a physical thing and then the convergence of digital world. 16 years ago when we started theCUBE, the most innovative thing with and Flash was like an adapter card, remember? And a server. Now it's scaled up. Now you're talking about innovation inside the service. Now, and the data center challenge and the storage and memory are important because everyone has to squeeze as much resource out of the physical plant of the data center. This is huge, Cynthia, because when you look at the standards, go back to Open Compute when it started, what, 12 years ago? I can't remember what year it was, but it seemed like about
just did year 14.
Year 14, oh, close.
Very close.
But it was, the concept was, let's get rack standards, basic stuff. Now with cooling, if you don't have the right components, rack being one of them, and storage, this is a big deal. So Flash for AI is here. The racks are getting set up to handle the power, handle the cooling. What's your take on all this?
Well, when we look at how AI workloads are influencing how we design Flash, actually it's very different across the whole data pipeline or the AI life cycle. So for example, during training, our systems are learning from huge data sets. So you need these high performance SSDs for model checkpointing and caching. And then you need these high capacity drives to act like fast data lakes. But then in data prep and ingestion, you need both the high performance and capacity to keep the GPUs fed. But when we look at inference, for example, inference is very different. Inference is a mostly read-intensive workload. They're often pipelined and sequential. You're both basically just streaming the model data to the accelerators. But inference is now spreading from data centers to the edge. So for inference, you start to care about efficiency, power, or density. So all of this starts to matter. But then when we're looking at Flash design, Flash has to handle all of this. So Flash architectures are also evolving. And Flash architectures evolving, especially around some new technologies such as CBA. That's what we call a CMOS-bonded-to-array technology. And that allows us to basically fabricate a CMOS wafer and an array wafer separately, so they each get their optimum conditions. then you bond it together to create the NAND wafer. And that gives us benefits of increasing cell performance, I/O performance. It lowers our cycle time. It gives us operational flexibility. And all of this is exactly what we need to meet all these fast-moving AI workloads.
On the standard side, I mean, how does that relate to what she said? Because that's like, we're getting very nerdy on the wafer and these chips. Connect the dots, Amber, because like in a system design, it all matters, right? So like a lot of people can't get their heads around like, okay, rack standards, I got a data center, hyperscale's been doing this for a while. Where's this crossover? Where's the dots connect on this and to like say the standards body? What's the most important thing?
I would say that the top most important thing is software. And so if we think about NVM Express, or we think about what you talk to as the interface of commands to the flash itself, that has to be determined a priori, because that firmware or that software, that is critical. And that's what allows you to get time to market and scale, because, hey, do I have an NVMe driver in every out-of-box experience? Then I would say the next thing is the physical form factor. So if we think about M.2, if we think about EDSFF, I did a bunch of those standards in my time at Intel, and they continue to proliferate, whether it was serial ATA or PCI Express or new interfaces that come on top of it. So I think that's where it really comes into play, is that abstraction of how does software or firmware talk to things, because software and firmware and changing that in the infrastructure takes a long time. And then the other piece is that physical connectivity of where does the flash plug in or whatnot. And you don't have to worry so much about all that bonding, because Sandisk is going to figure that out.
You mentioned Intel. Andy Grove, I always quote Andy Grove on theCUBE. He had a phrase, let chaos reign, then reign in the chaos. Yep. And this is where I think the standards conversation is super important, and I've been very, very much shouting from the digital mountaintops on this one. They matter because it's a systems design we're talking about here. Share your thoughts on what we're reining in, because you want an innovation to run a little bit and then rein it in by making it so it's operational. Explain why standards are super important right now.
Standards are super important right now because of the time to market and scale. And so if you're having to design every single piece of a system end to end and it's proprietary, that's going to take a longer time, and only a few people have the capability to do that full end-to-end proprietary system. So what we have with standards is each of us can play our part. And so that's what I really look at is, for example, some of the standards that we need right now is, how do I have a scale-up interface that works well, that I can talk accelerator, so I can plug in this company's accelerator or that company's accelerator and have interoperability. So for example, Ultra Accelerator Link is an interesting new consortia that's developing something in that space. So that's how we can break it apart and have these flexible, the models are changing so fast. Hardware needs to be able to change at that speed, and the only way you can do that is interoperability.
I think we might have coined a new term 2 panels ago called renewable hardware, because the concept came up where you can still build on old hardware on top of others. Cynthia, the concept of models changing and standards matter, because if you're going to scale up and there's a extra hop, or there's packet loss, or something happened between feeding the GPU, I call feeding the beast, that fails. So that matters, right? So you can't just like hand wave, so we use this new thing, and if it doesn't fit, explain that concept, because this is where like it's a critical fail. It doesn't look, it's hard to see, but explain that nuance.
Yeah, I think that's definitely true. So back to the standards point, right? Standards are especially important when you want the industry to adopt a new technology, right? And so it touches some of what Amber already commented. It's about compatibility, scalability, and how you can seamlessly integrate into the whole ecosystem. And this is more so important for new technologies. So flash might be something that's already well defined, but we have new technologies emerging, such as high bandwidth flash, which I'd love to talk about a little bit. But such new technologies might require like an industry-wide collaboration for adoption and alignment, because every little piece matters, not just how you talk to the device, but also how you hardware integrate it, like you described, right? So to that extent, like a lot of work has to be surrounding new technologies, and some of our work around making HBF, our new technology, be more adoptable for the industry is announcing things like a technical advisory board. We recently formed one that would include industry experts, senior technical leadership from both within and outside the company that can sort of help guide the development and strategy of a new technology development. And so something like that, including we recently signed a MOU with SK Hynix. So we will jointly establish and define a standardized spec for our new technology, HBF, and that we hope will enable more of our industry partners, vendors, customers to sort of join in and help standardize this, accelerate the path for industry-wide adoption.
Well, let's talk about those new technologies, because I'll just set it up by saying I was talking with a Broadcom executive here on their Tomahawk 6 launch, which had massive speed improvements, had some scale-up benefits. They were very much open standards focused, and the conversation was, what does standards give you? And they talked about some of the things around models have different use cases based upon the generative nature of it, which affect memory usage, and of course, you know, the use of the power of the GPUs and XPUs. But they didn't talk about the new technologies because I couldn't get it out of them. But so generative AI has some unique capabilities that change the nature of how memories, when and where. So talk about that as a setup into why the new technologies matter and what they fill, what gaps do they fill, or what advancements does it bring?
Sure. As we all know, AI models are just exponentially growing, right? So with these larger, more complex models, the workloads are demanding much more bandwidth and asking for significantly higher memory capacity. And this is something that traditional HBMs, high bandwidth memory, that use DRAM-based technology at its core, they can't deliver at scale, either economically or physically. So this discrepancy is sort of known as the memory wall. Everyone knows this, it's well known. Yeah. But if we look at,
we all know, hit the memory wall.
We hit the wall.
It's dreaded.
But if we take a deeper look at the recent release LLM models, there are some trends that we can actually observe. So one is model size is growing, expected, generation after generation, it's growing larger. The large ones could reach hundreds of billions of parameters to trillions. The second is that context lengths are increasing. So what that means is it allows the model to retain more of the past interactions. Context lengths are also increasing, so that allows the models to retain a lot of your past interaction information so that it can provide better responses over the conversations, longer conversations that you had or documents. So both of these trends actually require much higher memory capacity to store all that information. At the same time, we see some architectural innovations like mixture of experts. So what that means is you still have to store the whole model in memory capacity, but you only activate a subset of those experts for each token. So that requires less compute, less memory bandwidth for inference. So this sort of combination of needing higher memory capacity and lower compute bandwidth requirements, we call a memory-centric AI.
So mixture of experts brought that up because that's the key to the reasoning, which is where the inference is coming in, just for the folks who will connect the dots there. That's a huge deal. Okay, what's the new technologies? Can you share what some of the standards you mentioned a little bit earlier? How does that translate into what's coming next, and how does the standards, what's the momentum, and what's the current state of the union?
All right, so we're working on this high bandwidth flash, or we call it HBF. This new memory technology is very well suited for this memory-centric AI architecture that targets inference workloads, which will be around 70% of all the AI systems due to the increase in Gen AI adoption across consumers and businesses. It's built on our CBA platform, so that allows us to take a mature NAND array process technology and then bond it to a highly optimized, redesigned for maximum parallelism CMOS wafer and achieve the bandwidth we need. So with that, we were able to achieve bandwidth that matches HBM, but at 8 to 16 times the memory capacity. And it doesn't just stop there. So we're leveraging NAND flash. So what that means is HBF doesn't have to reinvent the memory media. So it's a technology that's now. And NAND technology being the most scalable semiconductor technology, it means HBF capacity, performance can continue to follow the gains of whatever the NAND flash roadmap can provide.
So you break down the wall. So it's like we all done construction in our house, like, hey, let's open up the kitchen to the living room. That's essentially what you're doing.
That's right.
Amber, talk about the impact now. Okay, now you're seeing a lot of things, OCP and then other standards. What's the landscape look like to make this happen? Things like this are happening. This is one use case. What's the standards have to do? What's the momentum? Are there any blockers? Is it all accelerated momentum? What's the standards position on this and what has to happen?
Well, I think that just touching on what Cynthia's already covered, if you look at the approach that's being taken with HBF, it's to leverage things like the HBM interface that's already standardized at JEDEC. It's to leverage flash that's already standardized. And it is trying to avoid the PCI Express bottleneck. So one of the challenges we've had with use cases like what Cynthia's describing is that you can't get all the power when you try to move all that data over PCI Express. That's a really big problem. So you lose a lot of the gains if you have to transfer it all over PCI Express. So some of the opportunities that I see moving forward are, number one, we do need a better interface that is coherent, that's higher bandwidth, that's lower latency when we think about host to accelerator, because PCIe is an amazing standard that's served us for 2 or 3 decades, but it is getting longer in the, how do you evolve a little bit long in the tooth? I don't want to, I love my PCIe friends.
Yeah, that's okay. That's evolution.
So that's one. I talked about earlier with liquid cooling. Now we're doing liquid cooling everywhere. Google's been doing liquid cooling for 10 years. We've contributed our cooling distribution unit design to Open Compute, and now people can take advantage of that everywhere. So that's another critical one of how does that spread. Other standards that are going to be really critical as we move forward, things like how do we just keep evolving HBM? So HBM4E is out today. How do we get to HBM5? DDR6 is in active definition right now. And so it's all this natural evolution of how do we just keep moving forward. But I would say the biggest key is how do we move forward faster? So traditional standards bodies will take 2 years where you're arguing over where periods are in sentences. We need to really get out of that.
All right, so you're on one template. I think OCP, we talked about before it came on camera. I think that's a template. Talk about what's the new format, what's the new, I guess, best practice or protocol for standards bodies to move fast in the high demand area. I mean, you have to kind of let the fashion wars go to the sidelines. You can't, this is at least my opinion, but what's your take?
So my take is we need to get together and identify the areas that are non-differentiating toil, and why are we just doing things differently because we never talked? Like, that's kind of not very smart, right? And so one of the things we've broken down the walls is how do we come together? So something as what is mundane as how do I do firmware update for a GPU? We pulled together NVIDIA, AMD, Meta, Google, Microsoft, and just said, let's write it down. And why should that change every generation, which it was before? So those are the types of things that impact time to market. So what we're doing is, what Open Compute Project does is gives us a very flexible place where 5 companies, 2 companies, 7 companies, whatever it is, the stakeholders can get together, decide this is a problem to go solve, and I'm going to write that down. We just did that with Meta and Microsoft and Google on plus minus 400 volt data center, not data center, DC, there's too many DCs, but DC power delivery. And so that was really useful of coming together on the electrical and the mechanical interfaces, and now we can leverage common supply chain of people can build something that will work for any of us. So
cost, time to market, all those value points.
Exactly. We come together for 6 months, and in that one, for example, we couldn't agree exactly on where you measure the impedance point. So we gave a couple options in the spec, and that's okay. But we agreed on 90%, and so the supply chain can move forward. So we're pretty excited.
That's awesome. What are you most excited about? Since we got my mind rolling on the momentum, it's pretty phenomenal. What's in your mind? What's most exciting right now in terms of some of the standards activities that has your attention? It could be a pet project. You don't need to offend anyone, but you can pick a favorite.
What's most exciting to me is traditionally we've always looked at the standards from IT rack and down, or at the component level of whether we talk CXL or other things like that, or DDR. It's now IT rack to the data center. So how can I build a data center shell that can take anybody's infrastructure? Because trying to decide, from Google as an example, how do I decide whether I'm going to put a TPU or a GPU from one of the vendors into my facility? I don't want to have to decide that 6 months ahead because I don't know what the demand signals are going to be. So a really big thing is agile and fungible data centers that we can figure out the cooling, the server halls, how do we do robotics within there for servicing the racks?
Yeah.
That's
the old days, I called it plug and play. I'm drop shipping data centers. I was quoting someone's like, you could drop ship data center into a country. I mean, this is the large scale we're talking about. The data center is the computer. That's where it's going. Cynthia, so what are you most excited about? You have the new technology. You know memory is the hottest area right now. We were talking about solid state and devices and flash 2 years ago saying, wouldn't that be great if it was a primary memory tier? It's happening. HBM is not the only game in town, but super critical. You got DDR. So like memory's hot. What do you pick your favorite?
Well, my favorite has to be high bandwidth flash right now.
Of course, yeah.
We're disrupting the world with high bandwidth flash because when we look at how the current data centers or all the GPUs working on AI models work, we know that the DRAM-based HBM's sort of capacity scaling is stagnant. So if you have very limited amount of memory that you can fit in one GPU. So if I were to run a large foundational AI model like GPT, the only option I have is to split it across multiple GPUs, and that incurs very high system costs. Not only are these GPUs super power hungry, and now I have to move data across, so that also contributes to a significant portion of the overall system power. But with our HBF technology, we said that we're delivering 8 to 16 times the capacity at the same bandwidth. So now you have the ability to bundle terabytes of memory in one GPU and store the whole model in one. You can also imagine systems that might start partitioning the inference workflow into something that is compute intensive using HBMs, something that's more memory intensive using HBFs, and provide like a better balance of energy efficiency. And so our HBF technology doesn't just stop at the hyperscalers. So for edge applications, it's able to enable very sophisticated AI models that currently aren't possible at the edge. It could be either due to cost, power, or even space limitations.
Yeah. What I love about this conversation is innovation and open ecosystems together work well, because if you can bring in that enablement, what happens next is people get smart. The toil's getting taken away, all that, oh, I didn't update the firmware. Oh, the hassles go away as an example. And so that's going to create creativity. You brought up the edge, because the edge is one of the most explosive, because right now there's not a lot of training at the edge. There's inference at the edge, but no training. But I'd imagine as the ecosystems figure it out, some smart vendor, smart entrepreneur might say, hey, I can take the flash HFS, HBF, not HMB, and put it on a small little, like a fire detector-like device size, and make that a high compute node. Now that's cool.
Very cool.
How far are we from that? Because that's where the action happens. Imagine retail or any kind of vertical hospital where it can upload your location, do some inference and training off the new data, pull down models. Because what you're getting at is here, the segmentation is about resource allocation. That's an operating system. I mean, that's what we're getting at the point now. This is now a large-scale system. How fast are we going to have that out?
Well, I think it's very cool because like something like HBF, right? It's sort of redefining the AI memory with massive capacity, but at minimal footprint. So now the systems that actually adopt this memory-centric AI will be able to provide longer contexts at lower latency, at lower power and cost. And so that gives user like a faster, more accurate, more private AI experience. With this new HBF technology, right, what we would see next is that you could be moving from a prompt-based interaction to something that's a purpose-driven intelligence. So today's models, they respond based off a isolated single prompt. So they'll forget all the conversations that you just had with it. But future AI can operate with intent, persistence, memory. So enabled by these high capacity, low latency memories, now the systems will have persistent memory. It can remember you. It'll continuously learn everything about you and adapt to your user experiences and provide you with responses that sort of align more to your long-term goals rather than a single prompt. So you can think about it like having your own personal AI wingman.
Yeah.
And I think that's where the context and having the context with you is how much do you need the training at the edge versus that context, and then it can adapt to you is a really critical piece.
Yeah, I mean, it's just intelligent. Final question for you guys. I mean, I feel like it's like we're in an era now where we're going to see a huge step function change. What's the future look like? What do you guys see as blockers or enablers, that blockers to move away or enablers to double down on for this race for that intelligent edge, full, I mean, it's funny, memory's been used term like GPT has memory, and then you got memory, like sometimes I get confused between who's got what memory problem. But what are some of the future things that you guys see that, and maybe add like, what does success look like or not look like? Because a lot of people are confused, like, well, that seems like a good approach on paper, this proprietary thing or a unique approach. But we know the history, open wins every time. That seems to be the winning hand. So just what's your future view of this world?
I would go with heterogeneity. So already we're seeing a lot of heterogeneity of whether we think about TPUs, CPUs, everybody's favorite of what they collect and put together. And so with that heterogeneity, now I'm not waiting for, if the models are moving every 3 months, every 6 months, every 2 months, they're moving so quickly, the chip design needs to move at that speed too. So one thing that we're excited about at Google is the thought of AI for chip design. And so we've been doing a lot of work on auto placement. How do you think about, one thing I'm really excited about is AI for standards, because today, a lot of times we end up with a chip spin where we try to plug in IP from 2 different vendors, and they each interpreted the spec wrong.
Yeah.
And so if we can get to where we have a common language of, hey, I can actually tell that this IP complies to the standard and will work end to end, these are the kind of things where we can go much faster in the heterogeneous of how do things go, because Moore's Law is not what it used to be. Yeah. And so we need to figure out how to really
that's a human problem too,
design.
Getting agreement on what people's biases might have been. I agreed to that. No, not really, you didn't agree. And also, I was talking to a friend about 3D printing. When I first saw a 3D printer, I'm like, oh my God, that's amazing. It's the coolest thing I've ever seen. Where's the 3D printing for chips?
Exactly.
That's going to come soon. It's got to be here.
I hope
that could solve the foundry problem.
It would, and then we'll keep innovating in that direction. We have our CBA now. It gives us flexibility. We'll continue to move into the printing.
Well, I mean, I just bring it because innovation could come from anywhere. You don't know where it's going to come from. Thank you so much for coming on. I appreciate it. Great conversation. Data and AI and data movement, one of the big things. We're doing our part, bringing the data here in theCUBE. I'm John Furrier. Thanks for watching.